We're going to go into what's called organic chemistry, okay? So this is the sort of thing that terrifies people if you're taking the full organic chemistry class that takes a whole year. It's pretty intense, but the good thing is when you're done, you know how to make stuff, like literally how to make stuff. Like you want to break bad, you could do that, you know, if you take organic chemistry. Or break good, you know, you can make things that can help mankind as well. Polymers, plastics, all sorts of stuff. So I want to just kind of introduce kind of the just fundamental ideas, because I don't know that students always get this picture of what organic chemistry really is. So I would probably say it's mostly about us. It has to do, we have a kind of a whole branch of chemistry designated around covalent chemistry. It really came out of this corner of the periodic table because we, or living things as we know them, are really made out of hydrogen, oxygen, and carbon, predominantly. So because of that, we have this whole branch of how this carbon molecule bonds and makes all these molecules. So what do I mean by that? Like, literally, I mean, short of like calcium for your bones, you are, you know, your carbohydrates, your proteins, your amino acids, your nucleic acids, it's all made out of carbon, oxygen, and nitrogen, hydrogen. Okay? So, kind of all covalent bonding side of the world. Does that make sense? So, because of that, we kind of, you know, we give it its own designation. It's stuff like fuels, food and medicines, of course, what living things are made of, and then plastics and polymers, and that's why I've got Stephanie Kulik up here, because she's got her Nomex gloves on, which are fireproof, and she also invented bulletproof, right? Those are polymers, right? So she invented bulletproof plastics as well. So, you know, you guys also are interested in polymers, like the Invisaligns, right? So that would make sense. So, how do you start talking about organic chemistry? Kind of get it as simple as you can without being like, I'm not trying to be, you know, gotta be useful to you, right? You gotta understand it. Well, here's what I'd say. Organic chemicals are like, when I look out in the car lot, I see all these different automobiles. You with me? Everything out there has a frame, and that's all fundamentally the same. And then you put something on it, right? And it makes it unique, what it does. Tracking with me there? So if you take that analogy to what an organic chemical is, I'll just jump out of that. Every organic chemical has a hydrocarbon frame. It all has carbon and hydrogen in its, what we call it, you may hear it called substrate or backbone. So I would write those down. And it's just literally, and is everybody okay with that term? When I say hydrocarbon, you hear hydrogen and carbon, right? So that, there you go. So we need to be able to read it a little bit. So let's get a couple things out of the way. Because the backbone is on everything, right? And I want you to focus on the functional group. In chemistry, we have a way of putting a backbone in and just saying, it's there. And it's just R. We put an R in there. Or as the pirates say, R! Yeah, they were all organic chemists. Okay, got it? So, on here I've got an alcohol. You could just say, well, there's some functional group. I don't know what it is. But there's an OH present, and that makes it an alcohol. Follow? To the right, if I had carbon chains on either side of the oxygen, that would be called an ether. You tracking? Seeing how this is laid out? Now, along there, look it down to amine, far right. R prime, you know, so you got an R prime, so I'm going to look down at the bottom. That R dot could mean R could be a hydrocarbon or just a single hydrogen. Do you see that? So I'm going to help you understand that. So just, for example, if I said that, I'm going to do amine, and I could say, well, there's a CH3, there's a very simple hydrocarbon. Follow? It's still an amine if I won't color my hands too much. See the single ring? Maybe it's back here in my office. But if I just do this and change it to H, it's still an amine. That's what they're saying with the R star. See it? So yeah, either one works. And that could be all changed up. I mean, it could be this. And by the way, when I do this, I'm not constricted to this, right? It could be 1,000,000 carbons on here. Doesn't matter. What the backbone looks like doesn't matter. It's just hydrocarbons. But the presence of that nitrogen kind of signals it's probably an amine. There's other things with nitrogen in them, right? So you got to be kind of selective about this. Look at, let's see what else we got in here. There's an amide. See it down and to the left? Kind of looks like an amine. The difference is that nitrogen's not connected to a hydrocarbon. It's connected to a very special carbon double bond oxygen. So that's a unique thing to look for in a lot of structures. See it? The carbon double bond oxygen? You see it in fact, that whole row across there. Amides have it. Aldehydes have it. Carboxylic acids have it. Ketones have it. It's really what's connected to that C double bond O that makes it the group it is. So that'll take a little minute to get used to. If it's just a couple hydrocarbon chains, who can tell me what it's called? C double bond O with just hydrocarbon chains attached to the C double bond O. Just throw it out there. We're learning together. Anybody? No? Ether. So everybody look at ether. Where's ether at? I want to name one of my daughters ether. No. So C double bond O, right? See that look, that ether is just a single bond. You see there's just a single bond? So we're looking for this thing. There you go. See them? Everybody see them? C double bond O? If I have two R groups attached, or hydrocarbons, and that's all that's attached, what's that called? Ketone. You see it now? Everybody look at the ketone? Now, if one of those got replaced, instead of just being a hydrocarbon, there's a hydrocarbon on one side and the other is an H. That's a unique group. What's that called? What's that?
Aldehyde.
Aldehyde, yeah. And so, if you've been around some different medical conditions, you'll talk about stuff, especially people that are diabetic or whatever, they talk about ketones being formed when their alcohol or their sugar is starting to go through reduction. But anyway, that's a ketone. You might hear that term. Right now you know what that means, right? Cool. So we're going to get used to a little bit of that. It'll take a minute to get used to reading it, but we're going to work on that. That'll be the functional groups. I got a whole group. I'm going to kind of run you through a few things. Okay? If you don't have anything attached at all, there's still a special name for that. In other words, it's just a hydrocarbon chain. Nothing special. We just call it an alkane. This is just straight hydrocarbon chains, no double bonds, no triple bonds. It's just single bonded. We call it an alkane. All right? Here's an example. See this guy right here? There's a carbon. Remember, carbon bonds to how many things? 4. So really, and then hydrogen's never connected. How many things is hydrogen connected? 1. So this can be confusing because sometimes students are going like, oh, I've got H's connecting 2 carbons, but that's not what that means. It means I've got carbon bound to carbon bound to carbon, and these carbons have this many H's on it. So you kind of got to get used to that with hydrogens. They get kind of stuck in there and they can be confusing, but they're basically, the H's are attached to the carbon. The carbons are bound to each other. So this is a 3-carbon chain. Okay? But you'll hear the word A-N-E, that's kind of your clue. Oh, A-N-E, that clues me into just a straight hydrocarbon chain. So you go to the gas station, you look on the pump and it says octane. You're like, oh, how many carbons is that? 8, and that's it. It's an 8-carbon straight chain. See how that's working? All right. What's butane in my butane lighter? Uh-oh, help me out. This, you might be going, why not over here? Let's do it first. Same thing, the molecule flips is the exact same thing. So, but you'll learn a little of that, don't worry. Don't overstress that piece right now. Just, let's keep it simple to get started, right? How many H's should be attached here? 3. So if I was drawing it in detail, I would be going, okay, there's 3 H's. Now how many H's should be attached? Careful on this one. How many bonds am I counting on there? 1, 2, 3. So how many's left? 1, yeah. So it goes CH, and then that doubles off to this. That has 2 taken care of. How many leftovers?
2.
2. And there you go. There's the true Lewis dot structure of propene. So it can get hard, or you can keep it very simple and just go, look, every carbon has 4 things. You know, if there's a line already occupying it, that's 1 down, right? And that's all we're doing. So far we've learned the this is the backbone, right? These are just backbones so far. We have alkanes, we have alkenes, and then last we can do, and then by the way, I'm going to just give you a little bit, you know, since we're learning them and you haven't really talked about them or don't know much about them. I'm running around uncapping every marker I have. This is amazing how much if I didn't do that. Probably like, I've got all those markers open. All right. This alkenes you might have, it's a key to saturated and unsaturated fats. So this we will come back to and learn later, so you might as well learn it now. Like I'm not going to hold, you know, you'll see this later. But saturated means it has as much as it can hold. Okay? You with me? So here's the idea. Yeah? You ready? How many hydrogens on this?
3.
3. Now I'm going to kind of bust out to a little different notation. Just now I'm getting lazy already. Save myself some time. How many H's on this one? 2. Right? Now do you see why they're doing that? They're just trying to avoid drawing all those ups and downs. How many on the end? 3. By the way, I messed that up. I saw you squint at that. That's probably why, because that was wrong. How's that? Better? There you go. Is that okay?
Does it matter that that's H3C and the rest is CH? Like the same?
Thanks for asking that. Doesn't really matter. You see them get flipped both sides, and the thing is, it's assumed that chemistry students know H is never connecting anything, so it can only be attached to that carbon it's near.
Oh.
Thank you for asking that, though. And I'm sorry we're not consistent with that. But sometimes we just let computers draw it for us, and they just pop them on one side or the other, and it just happens so frequently, I just sooner get used to it than me try and be very, very consistent, and then books and everything else aren't. It's a good question, though. I think if you're trying to be very accurate, the correct thing to do would be put them on the right.
Okay.
But it ain't gonna happen. So I just don't want to disappoint you. I'll end up both sides. Good? Now watch. I hope I didn't get you way too lost because you guys were already on this, but it's saturated versus unsaturated. Saturated means this: it's got as many hydrogens as it can hold. In other words, I only have singles and everything else is H's, but the minute I start introducing a double bond, then the number of H's drops to what on this carbon? 2. So it doesn't hold as many H's as it did before because it used to hold 3. Follow? And this guy, he only holds how many H's? 1, and that's where the term unsaturated means. I'm not saturated with hydrogens the way I was before. If you want to keep it simple, you go, the presence of a double or triple bond makes it unsaturated. That's fair. It's easy enough, but I just kind of wanted you to know the root of where that term came from. Does that make sense? Saturated means as many hydrogens that you could load on there, which would mean it's all single bonded, because that gets more H's on. Once the doubles and triples show up, you lose H's. Right? Watch this one. Let's do a triple. I never finished this out. That didn't change, right? But let's do a triple on there. Watch this. And if I did that, right, that's the next family, by the way. By the way, this is used in a lot of polymers. They use that a lot. Talk about that, but here's one. There's a triple bond. That's called an alkyne. Now all we do is put an YNE in there. Once I see that in the name, I go, oh, there's a triple bond. Okay? So ethine, I know, oh, there's 2 carbons, 1 triple bond. But let's just look at this. How many H's could be hanging out on the end of this? Only 1. That's right. How many H's could be hanging out on this one? Count again.
On the end one?
None. Yeah. It's full. So then this one could have the 3, but this has none on it. And that's where that term, right? I'm unsaturated. I don't have many hydrogens. That's all that is. And that will come up again when we get to biochemistry, because saturated and unsaturated fats are part of your nutrition education, kind of understanding the difference between them. Interesting stuff like ethanol estradiol birth control, or some sort of poisons in frogs. They have triple bonds in it. Just trying to make something out of that. Still side facts. This is a very unique bond. It's really alkenes, right? If I agree there's double bonds, so you go, oh, that's an alkene. But when you circle it up and make it a 6-membered ring, it's very prevalent in nature, so it gets its own term. They call it an aromatic group. Very unique. 6-carbon ring. You guys see it down at the bottom? They're calling it an aromatic. I call it an aromatic, and they're in the sheet, what are they calling it? Arene. So underneath that on your sheet, put aromatic too. That's a common phrase. Now, the way I've drawn it, it has H's on it, correct? But if you look at the sheet down below, that R star means hydrocarbons or H's, either one. Just that 6-member ring with that alternating double single, that's a special kind of ring. It's flat. It has its own electronic signal. It's really wild. It's very stable. Just, in other words, there's chemistry that double bonds will do, these won't do. There's something unique about the stability of that ring. That's crazy high-level chemistry when you really get into it, but it's kind of cool. It's called the aromatic system. But it's very prevalent in your living systems. So we talk about it. But the thing you might get out of that is that alternating double single and the 6-member ring, it leads to extra stability. And again, we're just learning chemistry words, right? So when I say stability, that means not very reactive. And that could be good in the body, right? It might be part of the structure, but I don't want it necessarily doing any chemistry. So it won't do normal alkene chemistry. Yeah, there I go. I just remind you guys. That's chemistry lingo, right? It's more stable, less reactive. That's unstable. That's very reactive. All right? All right. When you put, see there's an X group. Now it's kind of an odd one, right? There is no element on the table, periodic table with an X in it per se, except XE, but not a pure X, right? That's just a shortcut. It's just saying I could be anything out of this family right here. That's called the halogen family. See it on your sheet? see an acyl chloride. I'm like, how many mistakes do we have? Oh, here it is. It's haloalkanes. Halo, that should say haloalkane, not halocane. I don't know what happened there. It's missing an L between the A and K. Or an alkyl halide. That's how I would usually refer to it myself. Now, the reason they put an X instead of one of those, they're just saying it could be anything in that family. Okay? So, now you have another symbol that's kind of unique. R's mean it could be any kind of hydrocarbon. It's an R star, it could be any hydrocarbon, or H, it's interchangeable. And then now we have an X, which means anything out of the halogen family. Just an easy way to capture a lot. So, see how the naming, know how simple it's getting? How many carbons?
3.
Try one more time. 2. That thing's part of the
it's
chlorine.
methyl.
Yeah, it's tough, huh? So that's 1 chlorine and then 2 carbons. So the 2 carbons lead you to F. So they're just saying, oh, it's ethyl chloride. It's fairly simple naming once you kind of get the swing of things. Capture the backbone and then just tell me what the functional group is. So, again, I just point out, hey, this thing about the I floating around, it's not real common with like halogens, except you do kind of have some iodine compounds in your thyroid gland. But beyond that, it's the chlorine ions are common, right? Chlorides, like sodium chloride, totally common. But to have like a hydrocarbon chain attached to it, that's like, oh, I don't know what to do with that. Like I really don't. Ends up on my liver, and I'm gonna get it out of there somehow. All right, so here's this group. And again, it's not, it could be anything. It's R, right? Any hydrocarbon chain whatsoever. And once you see this OH, that's an alcohol. And in the naming, sometimes instead of saying, ethyl alcohol, that's very uncommon. What they do is just put an OL in the name. So it's now called ethanol. That means 3 carbons. Propanol, like you hear isopropanol, that implies there's 3 carbons, right, with an OH on there. Yes?
You got the ETH, but where does the YL come from?
Yeah, that's it's an old style group. We don't use that very much. So you don't have to worry about it. I know. A lot of different old naming systems. This is the common one that's very straightforward. Ethanol. Instead of ethane, we just change it to OL at the end, and that means alcohol.
And then A and OL is alcohol.
Yeah, it's just usually just the OL.
Oh.
Because remember, if it was just a straight carbon, we'd say ethane. And if it was a straight 3 carbon, we'd go propane. But if it's 3 carbons with an OH, we'd go propanol. And we'll get that. We'll come back through the names, by the way. I'm just getting you introduced right now. All right? So again, do you see that in these groups? And this is where I want to get you guys, where you start. Okay, I see all this, hydrocarbon. Oh, that. Now I can look on my chart and say, oh, that's an alcohol. Right? That's where I want to train you guys. Now this has 2 groups in it. What groups do you see? I see 2. What do I see? Anybody? Aromatic and a alcohol. That has 2 groups in it.
So an arrow.
Or an arene is the other thing that's on that list, right? And this is just an alcohol. It's got the alcohol kind of hanging out in the middle of the chain, right? So sometimes they just put R's in there. They're trying to be less distracting. About that. And I say, we're saying drinking alcohols and liquors, but don't forget right now we're using a lot for antibacterial, right? So if you have so what we're learning is if you keep the carbon chain somewhere below 4 carbons, it's actually fairly effective at killing things like COVID, right? So that's showing up everywhere. All right, this starts to look like an alcohol, only instead of ending with an H, it just puts another carbon chain, right? So you would call it ROR, right? And that was somebody brought this up a minute ago. That's called the ether group. This is the old, put a little on the cloth, put it in their head, like the science spy movies where people pass out. They come up behind them with a little handkerchief and they're like, fall asleep. That's these ethers. That'll do that to you. And they used to use ethers like in medical operations. So, if you guys are around dentists that are actually putting people to sleep, but they changed that now because that used to have a lot of headaches and stuff. So it wasn't great, but it used to work. But they don't do that anymore. They have a different flavor of, what do we call it? Anesthesia? I don't know why I'm having anesthesia. Thank you. I'm missing my S. There it was. Stuck on the TH. Okay, here's an amine. Just put an N in there. And like I pointed out, this could be, and look at your chart because it does it a little better. That could be H's, it could be R's. Doesn't matter, you just have a single nitrogen. Single nitrogen bound to three somethings, either hydrocarbon chains or H's. Those are called amines. And so here I'm just showing the variations, right? If you have one hydrocarbon chain, you end up with two hydrogens. If you have two hydrocarbon chains, you end up with one hydrogen. If you have three hydrocarbon chains, there's no hydrogens. Part of this take-home we know from Lewis structure. If I read the Lewis dot of nitrogen, I can only bond to three things. So in this case, the amines are bonding to hydrocarbon chains, right? It's called the amine group. These show up in a lot of mood-altering drugs. They're in the structure of opioids somewhere, usually. Also good for explosives. Aldehydes. All right, now this next section I want to really focus on this. Anytime I see the C double bond O, start there and see what's attached. Anytime I see C double bond O, I'm trying to identify structure. Start with that and see what's attached. Here it's attached to an R group and then an H. So look at your sheet. I think you're doing it like this, which would be an easier way to see it. Hey, any hydrocarbon, doesn't matter what's hanging out here, but if that C double bond O also has a single H, we call it an aldehyde. Sorry, I jumped the slide here. Now watch how I change it. You ready? Does everybody kind of have that and you see it on your sheet? That's the aldehyde. So yeah. Yep, I see the R group, but then the other thing's just an H. Now we're going to just go, what if I had two R's attached? Like that. That's called a ketone. And here's an example, acetone, like fingernail polish remover. Right? Anybody want to take a shot at what that fancy, the official name might be, though? How many carbons do you see?
Three.
Three carbons. All right. So then if I had three carbons, I'd start with what prefix? Prop. And then part of the name instead of OL, like all, so it's propanone. That's the official name for fingernail polish remover, propanone. But we commonly call it acetone. Another thing organic chemists are famous for, switching the name. Here's the truth of the matter, is most organic chemists, like if we're talking stuff, it would be structure-wise. I would never try and name it because it's just a waste of your time. The structures that you really, with new drugs and all that, they're so big and massive, if you're trying to name it, it'd be meaningless, so you draw the structure with line bond. Because everybody can communicate that way very quickly. So it's a very interesting chemistry because it's very symbolic. Like it's done with symbols. Right? Because everybody sees this in organic chemistry. It's a very simple symbol. They know exactly what it means. Right? Oh yeah, that's a ketone. 3 carbons, propanone, got it. And again, we're not there yet. thing I'll get to with you guys is like, having 3 carbons will give you a little bit of an indicator about how fast it reacts to say versus having 4 or 5 carbons, and what structure or what state it might like versus being 4 or 5 carbons. Follow? You haven't learned that yet, but you'll just learn. I'll show you something kind of sneaky about these that you can go, oh, short chains. I'll just tell you now, but we'll make logic out of it now. Short chains are usually gas. Long chains tend to be towards the solid state. But I'll make sense out of that later. Short chains are very reactive. Longer chains slow down the reactivities. Okay? But we'll get there. We'll get up. That'll make sense to you later. You'll go, oh, that's why. That makes perfect sense. Hopefully. Okay? Now, look, it almost looks like an alcohol, yeah? But like I said, anytime I see a carbon, this C double bond O, that's called a carbonyl group, by the way. Anytime I see that, I just go, hey, what's attached? Single H, aldehyde. Another R group, ketone. OH, that's a carboxylic acid. Not an alcohol. And again, you won't be memorizing, you'll be doing it by sight, and before long you'll work with them enough. Some will be familiar, but it's most important that you can find your way on this table, right, and name it. And the key here would be not trying to find all the little parts, but especially anytime I see this, work off of it and go, what's attached? An R group, okay, what's on the other side? An OH, carboxylic acid. And you don't even consider an alcohol. By the way, yeah, that's because the chemistry behind between the alcohol and this is totally different. The stuff you can do with this is totally different from what you do with the alcohol. These are organic acids. We know them for making food flavor, like the acetic acid and salsa. That's what gives it the bite, right? These are all weak acids. And also, they can be active enough, chain gets short. They act very fast. Has anybody ever been bit by a fire ant down south? They're little red ants. You step in them, and I mean, it's like you're bawling. Yeah, they hurt. They have little formic acid in them. Yeah, so it's just like this stuff's in there, hanging out. Now look how it changed. Your eye should go, that looks familiar. Oh, there's the R group. Oh, what's this? Oh, it's not an OH, it's an OR. And now it's got a new name. It's called ester. You could get away with naming it out of that. Some people do. I tried ether, but all right. And yeah, esters are very pleasant smelling. So a lot of times the stuff you smell that's pleasant has an ester in its structure. Pretty. See how this, now are you getting used to this? There's a C double bond O. I see an R group. I look on the other side and go, oh wait, that's an NH. That's like an amine, but it's not when it's connected to C double bond O. This is called an amide. This is very important for us because it's going to be part of one of the biomolecules that makes muscles, proteins, and amino acids. It's going to be foundational to that. Again, if I was being official, I would put R stars on there because it's either going to be an H or just a hydrocarbon chain hanging off that end. See how I put a couple H's on there? It could have been R's too. Could have been hydrocarbon chains. Still called an amide. And just to show you that, right? Those are all amides. What's the key feature? C double bond O connected directly to an N. That's an amide. I don't know why I have RNA and DNA in there, because that's just not right. I'm just wrong. That's it forms the backbone of proteins and amino acids. How about that? We will make that correct. Okay, This is starting to look, now I just sometimes remember it looks like same family, right? See, oxygen and sulfur, same family. So now we kind of have a similar grouping in organic chemistry where you have things that look like this, which are kind of like the alcohol, only it's just got sulfur in there. Those are called thiols. And that's why it almost sounds like alcohol. It's going to have the same, they have thiol in there. Sticky. That's what skunks release. We even put a little thiol in your gas, like your natural gas in the house, so that way if it leaks, your nose can detect it. It's so slight, like parts per million, it can just pick it up. So they purposely put it in there. Because it burns, and if it gets loose in the house, it'll stink. Because if it got loose in the house and it was just methane, you'd never smell it, and then you'd know what happened when it blew up. You'd be like, shoot, I should have turned my stove off. But this will smell, right? So you're not really smells like gas. It's like, no, you smells like the thiol that got stuck in the gas. Protect us. This is like an ether, right? Only now it's sulfur in the middle of the R's. Call those sulfides. Just getting you used to the chart. That's all I'm doing right now. For a minute. And then this is a pretty important one. This is a disulfide. And this does end up in your DNA and RNA. So we do these disulfide bridges. It also ends up in your hair. The difference between that disulfide, you can be a thiol and be straight hair. And then if they lock across, it'll start to curl your hair. That's the disulfide bond. This is sometimes when I'm uncurling hair, you break the disulfide bond. And if you get too crazy, you'll end up like me. So be careful how you break your bonds. Just warning everybody. I mean, really, last week I had very thick curly hair. It's also how they vulcanize tires. So that's kind of wild. And what that means by that is they, tires naturally have a lot of give and grab for the road, which we need on days when it's icy. But they used to be too grabby and too loose, and so sometimes if you sat your car outside in the hot day, when you got there, the tire was like grooved, like flat, like the pavement. When you drove off, it went ba-dum, 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 and then it'd loosen up and be a tire again. So they actually figured out how to strengthen that with just these disulfide bonds. But then once they did that, they couldn't recycle them very good. So there you go. Then they had to figure out how to get rid of them. So once I actually had a project for the Army, I was trying to desulfurize the whole pile of tires they had. That was like a job. Sounds like a party, doesn't it? So we did figure out a technology to do that. Just cost way too many dollars per gram. So it didn't work, but worth the try. Okay, here's a little practice. This is what the kind of stuff I'd like for you to be able to do. You look at this structure. Again, you mostly ignore the backbone, right? Except I see double bonds, that seems important. I see the ring, that seems important, right? I see the carbonyl group, I start looking on either side. Okay, so you guys, being the fine students that you are, I'll just let you come up here and draw on the board. I'll remember to lift this so you don't write on the screen. And somebody come up here and circle a name. Okay, I've got about 6 of these up here. So you kind of work in your groups here. See how we break this up. You guys get to be a single team, this team of 5 here. There's one team. 2, 3. You 2 are on your own today. 4. Is that right? So yeah, you're the group. So you guys got A, you got B, you got C, D, E, and F. You just go up there and circle what you see and say, oh, here's the functional group I see. All right? And then for another kind of a fun little side job while you're up here, When it comes to like the longest chain on there, so kind of getting used to this naming, the only thing that'll break out a long chain is rings will break chains, these disulfides will break them, and the carbonyl groups will certainly do it. But if you have a carbon, like a double bond or a triple bond, it just keeps going. So find your longest chain in here and take a shot at a name. Just like, you don't have to write the whole thing, but just put the prefix. So case in point, you ready? We'll all do this together. 1, 2, 3, 4. What's part of that name probably? Butte. Okay, just put that up there too. Now some of these will have a couple, because once you have that, it breaks it on two sides. So how many do you see on this side?
2.
And how many on this side?
2.
2, yeah. So that would be part of that. That chain might get broken. Let's just scratch that. Just find the longest chain. That'll be good practice for now. I'm just going to get you guys confused. No need. Find the longest chain.
No, I don't have it. It's completely over my head. Yeah. I couldn't do it, but I don't think I could do it. How are you doing? No, yeah, I'm not, I don't think I can do it.
Wait, what part?
I can't, honestly, I'm having a hard time with all of it.
Okay, well, let's start here. What do you see that's unique in this structure?
There's a double bond?
Okay, so now you go to your sheet. What's the double bond?
I don't know, there's a bond.
Yeah, so the one that's just a double bond within the chain, though. See, this is the ring double bond, so that doesn't count, right? And then these are all C double bond O, so that none of those apply. So show me your, where's the double bond within the chain? So remember, ours are just chains, right? Well, let's walk away through that. No, right? You with me?
Yeah.
So just keep going. Does any of these apply? Where's your first double bond you're coming to? Okay, so now that's a C double bond O, correct? That's not a, and look up there, that's CC.
Right.
So those don't apply. So you see those, you can keep skipping.
Okay, so none of the O's.
Yep, yep. Yep, perfect.
Here?
Yep, there you go. That's the group. That's a, what do you say? It's an alkene. So you walk up there and go, there's an alkene present.
Okay, so.
Now, yeah, and then just keep going. Now you get here, you go, okay, here's the hydrocarbon chain. And you're looking for that thing.
Yeah, but I don't know how to.
That's it, that's it.
I don't know
Yeah.
what this means. So this.
Good.
So R's mean carbon and hydrogen.
Yeah, just put alcohol and then say 1, 2, 3, 4 carbons, so you put a BUT up there.
Oh, okay, so I
Just to get used to it.
Yeah.
Well, it's the longest chain in here. It's a BUT. If you wanted, you could try the whole thing. But it's
Yeah, he was saying like what do you need the C double bond. You can write the C feature plus all these extra things on the inside of it. But no, these are C double bond.
that would be correct.
As well.
Your carbon count.
And there's a hydrogen.
That's it. All? No, just leave it B. Just leave it BUT for now. We're just trying to get the carbon chain. That's perfect. Aromatic group, arene, perfect. OCT, because they
I
see the
still don't get
longest.
all the switches, like what's what. So NH2, like I don't know what that is.
Okay, so what now?
We're on E. We're trying to do E. So we see that there's a double bond, but there's a bunch of those double bonds. It's double bond O. So we see that there's a bunch of those.
Okay, so we see a double bond O, and all I have to do to figure out what that is, I gotta go, okay, here's a hydrocarbon chain, so that's one thing, and then there's an N. So what's a C double bond O going to an N? What group is that?
And then I think I don't know, an N is a nitrogen.
Yeah, so you're good. There you go. C double bond O N. That's an amide. That's it. But you just to double check C double bond H. No. C double bond O H. No. C double bond O another carbon. Not a dill. See, none of these are C double bond O M except for this. So that's the amide right there. So that's unique. But then off to the other one, there's an NH all hanging by itself. See, there's a hydrocarbon chain. So what's that guy? So you got an amide. Go nail that one. Just circle it and call it. Cool. You getting there? Yeah. Who's got A? Okay. No, that's fine.
Good.
Are you guys working on A? Oh, F. Okay. Oh, yeah. So you got an aromatic. Cool. One down. Yeah, none of that. Oh, okay. Yeah, for you right now, just get the longest chain before it breaks off. Would be 3. And that's good. That's not. That is minor to what I want you to do right now. You know the aromatic, but what do you do with this guy down here? Yeah. So that when you see 2 salt, S is what do you call it? Ooh, did you get that on there? Yeah, it was nice on there. Where did you get it? Is that on there? Or did I leave it on?
Yeah.
You had good notes. You had good notes. Shoot.
So how is that E an amide if there's 2, off the 2 nitrogens, there's a hydrocarbon? If that's.
Yeah, except you're right. Anytime you see a star, it could be a hydrocarbon or an H.
Or an H.
Yes.
So because the H is on it, it's.
Yeah.
So, okay. But you were saying that there's another NH off this CH.
Yeah, so this is an amide, which you know, right? Now this guy's all by himself. What's the N with either H's or R's hanging out? Ends with 3. Yep. Amines on that one.
So how would you call it? What would you
You
call
just say amine. You just circle that piece.
And that's just a group?
Yep.
Okay, so there's not a whole word.
No, because they're not connected because there's a carbon in between them. So you have the chains in between them.
Yeah.
An aromatic and a disulfide. Cool. This wasn't on in your sheet, I realize. You guys, that's not in there, is it? Uh-oh, we better add that too, because that is actually important for the biochemistry. So in the sheet, it should look like this. It doesn't matter what it is, and we just call that a disulfide. Yes? Oh yeah, for right now.
Or is it always just butane?
No, let's do that together with everybody listening. So
Okay.
just sit tight. Let's all run through this. So who had this first one?
Okay.
It's because you wrote it on there as butane instead of butane.
Oh, I see. Sorry, just BUT. I apologize. I got carried away. That better? Thank you. Now I see what the confusion was. Oh, here it is. This is right here. Perfect. So all I want you to get out of this is mostly look at that and go, oh, that's an alkene. Everybody was okay with that? And then we're just practicing a little to get used to it. If I counted carbons, I go 1, 2, 3, 4. The longest continuous strand would have given me some sort of bute in there somewhere. Okay? And then later, if we do some naming, we might learn that that is actually bute. Ene is the key for the, but we're going to today I want you just naming functional groups, counting carbons. All right, you guys named this. You just didn't circle it, but this is good. I agree. Everybody agree with that? It's an alcohol because it's an ROH, so it's an alcohol. And then if I was going to name carbons again, I would count them and go 1, 2, 3, 4. There's a bute in there. This is butanol, but I'm just getting you used to like, hey, that's an alcohol. There's 4 carbons. Aromatic, they counted the carbons out of there, and I'm not going to argue with that right now. It doesn't matter, but technically you count this as a 2-carbon chain, but that doesn't matter. You guys, I'm mostly worried that you go up there and go aromatic. Perfect. Look at this. So this is great. When I see an R and I see another R, ketone. And then if I was counting carbons, 1, 2, 3, 4, 5, so somehow there's a pent in there. Right? So that would have pent in the structure somehow. This one's a little tough. So you guys had a tough one. Right? The first thing they identified was this carbonyl. They went R, NH. They go, aha, that's an amide. Perfect. This could be a little tricky, but if you realize there's a carbon in between, you go, oh, this is not connected to this. It's all by itself, and that's an amine. And if I was counting carbons, how many would this chain have?
2.
3, and that would have some sort of prop in its name, right? That's all. Just get you used to that. So this is great. They got an aromatic. They saw a disulfide. And there you go. And if I was counting carbons, that would also have 3. That's good. That's where you start. Beginnings of functional groups. Takes a minute. Some of them are hard to spot. There'll be plenty of practice. Oh. And again, if you want, you can watch that video I put that somebody else had done and it was on there. Kind of introduces you to functional groups again. Get you kind of used to looking for them. I just make this note. Sometimes people get real lazy with how they draw them in the structures. They sometimes do like this and just put a circle around. Sometimes they just do this with a line because it's very prevalent. Just a couple ideas to put in your notes. I'm going to skip some of this, except you've already got this. Carbon attaches to 4 things. The rest isn't that important. I'm going to get up to line bond drawing here. I think you're doing pretty good on this. Let's take a break, and when we get back, we will talk about this. We'll talk a little bit about polarity, because that's going to be important. And or hydrogen, right? And how do they share the electrons? What? Unequally, right? So that makes them polar, right? So again, we're going to do this. You ready? Help me with the demonstration. We're sharing the electron, but we're sharing unequally, and this electron's charged negative. So she's stronger than me. What's her charge becoming? Negative, and I'm becoming positive, and it makes a pole on the bond. Correct? So if I looked at this and I go, oh wait, chlorine shares the bond with carbon stronger than carbon is, it would make the chlorine negative and the carbon positive. Okay? Now that pole, that is the thing that, so you saw me grab water with a balloon, right? I brought the balloon by and stuck over it. That's what grabs is that it's an electrical force field. Yeah? So what we got to do is identify in organic molecules where they'll show up, because they're going to be real important for why things want to bond to each other. And it also defines why things stick together. Let me help you with some ideas with that. Like if I think about 2 molecules sticking together, right, and they don't break apart very good, like I should get the same molecule. We're talking about how they stick to themselves. There we go. Like if that pole had a positive and a negative end, and then that had a positive and negative end, they'd stick because opposites attract, right? And how hard it is to pull those apart determines what their boiling point is, or their melting point, right? If they stick really tight, they might be solid. But if I could melt them, they'd start spinning, they'd be liquid, and if I could break them either far apart, they'd be gas, correct? So identifying those little poles in there might help you understand something being solid, liquid, or gas. And that literally is what gives rise to things like, oh wow, it's solid state, that plastic's holding together right now, right? This plastic, the little molecules are in there holding to each other. Right? They might be side by side sticking in this way, and then if I heat them enough, they'll melt, and then they'll be liquid. And if I could heat them enough without burning, they would actually could turn to gas. Right? Water, same way. Right? Water likes to stick together. If you get it cool enough, it'll stick in the solid state. And if I could break that, I could have it in the liquid state. If I could break that, it'd be the gaseous state. You tracking? So this is going to be a key to understanding state, because I was telling you earlier, like, hey, state and rate, that's kind of important to this kind of things. All right, I'm going to put some importance on that for you guys, like right away, like, okay? Sometimes, like when you're talking medicine, and I want to administer things, and I want them to, like, patient take them up and they go quickly, I would think gaseous state, because that always goes in fast. Where if it was liquid, it goes a little slower, and if it went solid form, pills, it goes a little slower still yet. Right? Because it's just harder to get to the medicine unless it's loose and moving freely about like a gas. Does that kind of make sense to you a little bit? So state might be important for stuff like that. The other thing would obviously be, how you administer some things, like, things go on in polymer, they're liquid state, how do I turn them to the solid state? What kind of interactions are happening that way? Okay, so with that in mind, I'm going to teach you how to identify these kind of poles and things and say, because before we just knew the definition, you knew what a polar molecule was. Now you're going to be able to look at any kind of covalent, right? That's all the organics, they're all covalent, and go, there's poles in there. So those will stick together pretty good. All right? And the way to find them is just like this. It looks kind of like a stealth bomber on the edge of your periodic table. See it? When I see these kind of elements in the structure, I have the potential to create poles. You with me? So that's kind of the giveaway. So now let's go to our functional groups. And we can kind of start running down the road a little bit. So we go through the alkanes. Right? It's carbon and hydrogen. None of that's in the structure. So there's no dipoles in carbon and hydrogen. So the the hydrocarbon chains, they have no polarity. They don't stick together really good. And then if I take a very simple hydrocarbon, like methane, it's a single carbon. I go, it's gaseous at room temperature. You with me? Okay. So I go up, keep looking at your functional groups. Now I've got an alkene. Is any of these things present in there? Without overthinking it too much, it's pretty simple, right? No? Okay, I don't have to worry about it. There's no polarity, like there's no polar bonds in that structure. Okay, what about alkyl halide? Any of that stuff present? Yeah, in fact, the whole family, right? That's what an alkyl halide is. So that gives rise to a special polar piece that means it could bond to water, because water is also charged. It means it bonds to itself pretty good, so that might make it want to be kind of solid. Follow what I'm doing? Okay. What about all of that C double bond O's? Yeah, every one of those is polar. The C double bond O makes the molecule itself polar, doesn't it? And I don't know if you kind of, fingernail polish remover if you know this, but yeah, it's water soluble, right? It has a little bit of polarity to it. That's that ketone, right? You tracking with me? So that's kind of how you'd identify that. You're looking for these to be polar. And I don't have to go through every group, but you get this idea, right? That if I look in there and I see these, I go, there's polarity in the chain. Is that good? And those are called heteroatoms. And the nice thing is if I do any kind of abbreviation, right? Like I'm just trying to do my chain thing and I go, here's a disulfide. I have to draw those in. So those should alert your eye and you go, this has polarity. How do I know? Because I see a sulfur near a carbon. That'll make it polar. And these are all, by the way, the stronger polars. In our analogy, all these things over there, they're like her. They're strong. They pull away from me the little carbon. I'm like, I can't hold it. You with me? Okay. So that's the presence of polarity. And so we mark it like this. Remember on the last exam you learned, if you grabbed an electron like chlorine, and you grab the electron off of sodium completely, you have a negative charge, and I have a positive charge, a full negative charge. And I have a full positive charge, remember? So calcium 2 plus, right? It's lost electrons. It's lost 2 full electrons. It has a full +2 charge. But this business here, this kind of partial sharing, it's a slight charge. So we use this weird, it's kind of a Greek symbol. I think it's a lowercase delta, is what I think it is. Some of you might look on your phones and figure that out real quick. I can't remember, but. Do you understand what I mean when I say slight? It's like, electrically charged wise, right? I can get in here and I can go, oh yeah, this battery has electrical charge on it. And I can grab both ends. It's no big deal, right? That's like this. But on the other hand, if I walk over here to the light socket, what's about to happen to me?
Give me a shock.
Yeah, you're going to the hospital, right? You're like, whoa, that's a whole nother level. That is the +2 and minus we were talking about. That's why it gets a full sign on it without any kind of squiggly on it. That's all that means. So it's a partial charge, but it's enough. I can grab it with a balloon, right? You saw me grab water, correct? Does that make sense? Okay. So I'm going to just, I don't know whose calculator this is, but I just took out the batteries. Thank you. All right. So, why do we worry about that? Because if you're trying to dissolve something in water, most organic molecules aren't very soluble in water unless they have polarity. Because water is polar. So, what functional group's on there? Alcohol, perfect. How many carbons? I got one drawn, one implied. Is everybody starting to see that? So what's the root name of this? So that's ethanol. That's drinking alcohol. Is that soluble in water?
Yeah.
I hope so. Right? My beer doesn't separate, right? I don't like grab a beer and it's like vinegar and water, like, whoop, hey, what just happened, right? So you know that's water soluble, and that's why, because they're both polar. And so now you go, oh yeah, that negative oxygen is going to have an attraction for the hydrogens, and that negative oxygen there will attract that hydrogen, and they'll stick. What about this thing? Do you think that's water soluble? Yeah, it's polar, right? There you go. What about that thing? That's butane. You see poles? No. Is it water soluble? No. And that's like you've seen oil in water, right? We did that a little bit in class too. Remember I was drawing things that I couldn't pull with the balloon? Mixed them and they separated. That's what that's like. What about that? Yep, see the pole?
How do you see the pole again?
Yeah, what are you looking for? Right there, just look on that corner of the periodic table. Any of those little items will get you on there. So just the presence of any of those atoms. That one. See it? All carbon and hydrogen. Does that help? So really good. I want you to guys, thanks for asking. It's good to ask those kind of questions. Cool. Okay, we're going to do a little practice, and I'm just trying to show you. Same thing, we just went through all these. So we think ethanol is soluble, and I kind of have this just so you can kind of appreciate what happens, right? That would stick, and it would actually dissolve, right? That's why they go into solution. Water could bond this, and I've got it drawn right? Because the positive grabs the negative grabs the positive, right? It just dissolves it. Oh, nah, I got nothing to grab. And so you get two layers. This should dissolve, correct? Barely. Come on, you can do it. I just left it there. I don't know why I didn't move it. I was too lazy. Yeah, this will dissolve. Okay? All right with that? All right, I'm going to just run through this. This we've already started into, and I'm reviewing this, and you can use these slides, but we've already talked about this. We're talking about, okay, we know this, C4H10. We've learned these. You do single bonds to represent how many electrons? 2, correct? You might expand it up a little bit, so you could say, well, up here I can't really tell who's connected to who. I mean, I know there's 4 carbons, but are they connected to each other in a ring? Are they straight? I don't know. Are they branched? I don't know. But when we do this, I have all the detail I need to know, oh, these 3 are attached and this one branches. I couldn't tell that from here. Right? When I see this, for all I know, it's, I just don't know. So I don't have enough detail. Could have been like this. Carbon, 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 carbon. And then H is attached like that. I don't know just by looking at the formula. But this gives me enough detail to go, oh, actually 3 of them are connected and there's a little branch off that middle one. So this is more detailed, correct? And now this is called a condensed formula, which is not exactly right, because basically I'm supposed to show 4 carbons. There's 1, 2, no, I guess that's right. 3, 4, that's 4 carbons. So that shows the same thing. This is the, we use this a little bit. I'm trying to get you used to it, but we don't stress that much. So I won't be really drilling you guys on that. You'll see this, but we go from here to line bond. And that's the one we want to work with. See, now we're kind of getting less. That's partially condensed. Like, okay, I'm going to put the detail in, but I'm not going to show how every H is connected, right? And then that's the line bond. That's the thing we're after. Now, how many H's should be attached right here? Just do your counting. 1, right? 1, 2, 3 carbons. There's 1 left over, so 1 H attached. Sure enough. How many H's are attached on this?
3.
3. Follow? That's the line bond. And these are the ways we really work in organic chemistry. You see a little bit condensed, but I don't spend much time there because it's kind of a pain. Now, I will show you one little relationship that sometimes ends up being helpful. Like when you do just an alkane, the relationship between the carbons and hydrogens always ends up in this pattern. No matter how many carbons you have, if you take it times 2 plus 2, that's how many H's will be there. So if I only have single bonds, this will be true of how many H's end up on the total structure. That's just a little fun organic chemistry fact. So just like this one, I have 4 carbons, right? So I double it, add 2. So double it, it would be 8. I add 2, I get 10, and that's correct. That's C4H10. If I counted the hydrogens, I'd be correct. And even the branched ones work that way. They don't work if you close the circle, and they don't work if you have double and triple bonds. Just a side note. But that's a side note, because here's what I want you guys to learn. Every time there's an end, that's a carbon. Every time there's a bend, there's a carbon. Ends and bends are carbon, right? We've already learned that. That's what condensed would look like. If I wanted to put the double in, I have to draw it in with line bond drawing, yeah? And the H's automatically switch out. I lost an H by doing that, right? If I have anything besides carbon, I have to put it in, and when H's are attached to those, I have to draw them. So that makes it easy. I don't assume you know how many H's attached to that O.
So that means 1 H is attached to that O on that end.
Yeah, because I'd have to put that. And by the way, this is not a carbon here though, so be careful of that. That throws students off. That's actually that carbon leaving and attaching to oxygen. So how many carbons? 1, 2, 3. That's propanol.
And you can assume.
And by the way, wow, this is interesting. That structure is wrong right there. Because that has too many. That would be correct. All right? So again, we look at that and we go, okay. Whoops. What's assumed to be right there?
Carbon.
Carbon with how many hydrogens? Yep. Carbon with how many hydrogens?
2.
Carbon with how many hydrogens? 1, 2, 3, 4, so 0 hydrogens. So yeah, once you count 4 bonds, then there's no room for hydrogens. And this is good to look below and you can reference and go, oh yeah, anytime that's present and it's branching off, then I'm full. No H's. Now again, if I needed an H on there, I'd have to draw it. So this literally means there are no H's attached. So you don't have to worry about that. And same here. If there are H's attached, they have to be drawn. So that's kind of the end of that. Again, there is some condensed forms that show up. Don't let it throw you off. The H's are usually attached, not usually, but they should be the carbon in front. But as you pointed out, every once in a while, that gets flipped. Don't let that throw you off. If there's nothing in front of it, it's going to the left. But this is proper. That was done properly, the way that is right there. So there's that. But again, what would be the right way? How could we easily draw this thing? I take the longest chain, which is 3. Right? Whoops. And then there's one branch in the middle, and that's it. It's really simple. That's line bond drawing. And it doesn't matter, flipped up, flipped down, that doesn't matter. Because the molecules rotate in space. They twist and they turn all around. None of that matters. Okay, what I'd like for you guys to do is see if you can turn these into line bond structures. This would be good practice for you. And the key, let me help you get going on this. You ready? Count your longest chain. That's the secret, I think. So I'm going to start down here and I'm going to try and go continuously carbons as far as I can go. So there's 1, 2, 3, 4, 5, 6. That's the secret. You ready? 1, 2, 3, 4, 5, 6. Everybody tracking? And in fact, I'll even number them. Just to remind myself. See how I did that? Then once I have that in place, I go, the first branch is at carbon number 1, 2, 3. That makes it easy. See how I did it with numbering? And then the next branch is right next to it at 4. So I go to 4 and branch. I'm done. It's really helpful to number these things out. Now try this one on the right. See how you do. I'll be able to ask you guys a couple questions if you get your structure right. So count it, show me where your branches are, and then I'll ask and see how we do it here. Everybody, see if you can get it done. Ask whomever I want. You'll have it, I'm sure. How we doing? Just take a minute, okay? Ready? Longest carbon chain. 6. Does everybody see it? Just start on one end and keep going until I run out of carbons. 1, 2, 3, 4, 5, 6. So then we just 6 jiggles. So this is correct. I can work off this one, right? Wow, losing my voice over this dude. So this will work. Work off this, correct? What is that group hanging out of there? Alcohol. What is it branching off of?
The second carbon.
Carbon number
2.
2. Is that what you guys did? Then the next carbon branches at carbon number 3. Next branch at carbon number 4, and it has,
2.
it's got a carbon down and a
Chloride.
chlorine, which is that alkyl halide, right? And there's your structure. Good? Make a little practice. That's line bond drawing. What do you think the root name of this is if it's got 6 carbons?
Hex.
Hex. That's right. So we'll learn a little bit more about that naming, but that does have hexane in its root. So find the longest continuous chain and count them, and then show branches off the different carbons. So I'm just kind of walking you through, see how it's. Now look at this one. See how I did mine? Up and down. We put them both up, both down, up and down. Does not matter. Does not matter. Same idea. This is a little cleaner. Woo. Now, if I said draw to condense formulas, would you do that? And the key here is count how many things are attached to this carbon?
3.
3, so I've got 3 hydrogens missing, right? So it's CH3 hangs out in here, right? What hangs out in here?
CH2.
CH2, there you go. And again, I don't get too far down the road without going, okay, 1, 2, 3, 4, 5. This should have a 5 carbon chain. That's what I'm going to work off of. And then I'll do branches off of there. Now, the branches in condensed form can go like this. You know, you got CH3, CH2, and then that next C, how many H's are attached?
4.
None, so I'm going to just put a C, right? And then I can go, okay, that branches to one single CH3, and it also branches to CH2, CH3. That's a good one. That's a challenging one. I don't do much of this question. I do the opposite. That's what I'm more concerned you're able to do. And then, oh yeah, thank you. And then you got to end with, thank you. You're nailing it. Great. So this would be good practice. And again, they recommend you stretch out all your carbons and then attach the correct number of hydrogens onto them. And that works.
Could you go back to the one that we just did?
Yeah, actually that's what the slides are showing too.
Okay.
They're showing that all done.
I guess my question is the C, the with no hydrogen.
This one.
Yes. How do we count that?
Oh, how did you know that? Let's go back. It's this guy right here.
Right.
Count your bonds. 1, 2, 3, 4.
Oh.
Nothing left over.
Okay.
Good.
So,
Good.
will there-
Same thing here. How many hydrogens are attached?
4 or 0.
0. So that's going to be a single carbon branching out to all this stuff.
Will it ever be 5?
No. Did you guys hear that question? You can't ever bond 5 things to carbon, so that's a good question. So once you get that established, you know, always 4. The bonds that are there, the leftovers are hydrogen.
Okay.
And then this is good practice. And that's kind of the line bond business. Now, you kind of, and it's worth it. I think we needed to go through this again, right? You got that online. You got it now. You got practice. And you're going to get some more sheet, like an extra worksheet that you can just work on the side to just help with answers, like it shows you that. Because it takes a minute, but once you get used to using this notation, my keys are this, like out of today. If you count the number of carbons, you could assign that, just very roughly, not the full name, just that. I want you to be able to, do what we were just talking about. Count carbons and know how many H's are attached. And then the other thing is spot functional groups out of a structure. Like get into the structure and say, oh, I see an aldehyde, I see a ketone, I see an aromatic. So there'll be plenty of practice problems with that.
Okay.
And then when we get back together, we will discuss, I'm going to jump up, we'll be at slide 4. So we'll be into, on we go. Cool. Homework should be available now. You can start working on it right away. And then make sure you show up in office hours if you need help. And if you're retaking the test, it's going to become online and you'll take it the same way you just took the last one. I'll have an open date in which you can retake the test and take it home with the lockdown browser, etc.